Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Heute wir haben Professor Stefan WALDMANN aus Würzburg, and he will tell us about the convergence of star products, and it will be old and new, and I guess everything in between. Stefan, we are delighted to have you. It's your first time at our seminar. Alas, only virtually, so we cannot take you for dinner later on, but we have to start somewhere. So here you are. The Zoom is yours. Take it away.
Thank you very much, Piotr, for the invitation and also the kind introduction here. And yes, it's my first time in this seminar, and unfortunately, I'm not able to travel to Warsaw these days so easily. I'm super packed with teaching in this semester, so this was kind of the only way to do it. Yeah, so no, I hope no offense. Yeah, and yeah, so I might be a little bit off topic in this non-commutative geometry seminar, and I see all the people here on the list being involved very much in C-star algebras and operator algebraic techniques and these kind of things. So I hope you will allow me to kidnap you for a little journey into neighboring fields. Yeah, and so my expertise, if there is any, then it's maybe deformation quantization, and mainly formal deformation quantization, which I will review briefly. And in the last decade, maybe I became more and more interested in also in more topological analytical versions of formal deformation quantizations. And so that led to a program of understanding the convergence properties of these formal star products, which we know by many decades now. Yeah? The formal situation is very well known, and it is in some sense a quest to make contact with C-star algebraic formulations of quantum theory or non-commutative geometry or whatever you like. Yeah, so for me, C-star algebras arise in the context of quantum theory, but you may have other motivations to investigate them. Yeah, and so this quest is really to fill in the gap in between this very nice operator algebraic scenarios of C-star algebras or even von Neumann algebras, things like that. And on the other side, these formal deformation quantizations, which have no good analytical features whatsoever, but which are easy to get. Yeah? And in some sense, the story I would like to tell you here is that these formal star products you can get easily, you can understand them, you can classify them. There's a lot of stuff known for them. And C-star algebras, for me at least, are very hard to construct for specific geometries, for specific problems at hand. And so it might be advantageous to fill in this gap in between, because the step from formal star products to honest C-star algebras, that's a huge step, as we will see. Okay, so much of propaganda in advance, and again, thank you for the invitation here. So let me start with my first kind of introduction to formal deformation quantization. So what is that all about? Yeah, so the setting is one starts with a manifold and a Poisson structure. So that's a Poisson manifold. And what does mean a Poisson structure? That simply means we have a Poisson bracket for the algebra of smooth functions on M. Yeah, and so that's a nice geometric scenario, which one motivation to study that is classical mechanics. Yeah? In classical mechanics, you have a phase space. This would be our manifold. And so this would be phase space. And this would be the Poisson tensor. In classical mechanics, this phase space might be a cotangent bundle typically, and there you have a canonical Poisson tensor, which is even symplectic. So you're starting in the realm of symplectic geometry, And it's nevertheless a useful generalization to go to Poisson geometry in general. If you take a more algebraic point of view, then what matters is the structure on the smooth functions, and that's the Poisson bracket. And this Poisson bracket, well, doesn't care too much whether it's coming from a non-degenerate bivector field or one which might have degeneracies. Yeah? So whether it's symplectic or not is not so important from that perspective. Yeah, you have a Poisson algebra to start with. Yeah, and then the idea is that this is sort of the classical commutative world, let's say mechanical system, and now you want to quantize this into a reasonable quantum theory. So what you would like to replace is that this algebra A here, which is sort of the observable algebra, if you want to interpret this, this should become non-commutative. Yeah, this should become a quantum algebra. And the idea is, well, you ask the physicist colleagues what they would require, and they say, well, the non-commutativity of quantum mechanics is sort of controlled by two things. Yeah, there's on one hand, the non-commutativity is encoded in commutators, right? And so the one ingredient you need is a parameter h bar, so that's Planck's constant, which is 1 in natural units. Yeah, and you also need a Poisson bracket, because what physicists tell you is that sort of in a good approximation, the commutators should correspond to IH bar of the Poisson brackets of the observables, matching observables. So you have the same kind of observable energy, momentum, whatever, and in the quantum world and in the classical world. And if you take commutators of the quantum observables, they should sort of correspond to the IH bar times the Poisson bracket of their classical counterparts. And then this led to ideas of quantization, that one should get a kind of a Lie algebra homomorphism there, and so that was Dirac's original idea, and then one can show that that life is not so easy. This one cannot make this correspondence too precise. Yeah, and the problem, or one problem, is that if we focus only on commutators and Poisson brackets, we lose one very important ingredient, the associative multiplication. And as you all know, it is not the commutators, but it's the associative product which is responsible for spectra. Yeah, the question whether you have a spectral value of an algebra element is encoded in the associative structure only. Yeah, so you ask whether A minus lambda is invertible or not. That's a question for the associative product, but not for any sort of brackets. Yeah? So we also need for when it comes to spectra, we need an associative multiplication. So this has to be somehow part of the game, and of course we have a multiplication on the side of functions. That's the pointwise multiplication, that's commutative, and we expect the algebra of quantum observables to be non-commutative, but still being associative. Yeah? And so the point is then that the quantum theory, if you look out of the window, yeah, as I can do here, you don't see quantum theory. You see a classical world. Yeah? There are no superpositions. There are no funny quantum effects happening. This world is as Newton saw it. Yeah? It's classical mechanics, maybe classical field theory, but it's very classical. There are no quantum effects. If you want to observe quantum effects, you have to look very, very carefully. You have to do very precise measurements. You have to be very have a detailed look. Yeah. So from
so
what
there's no Schrödinger cat in your office.
Pardon?
There is no Schrödinger cat in your office.
In my
Schrödinger cat. You don't see Schrödinger
No,
cat.
no,
Yeah.
all cats are dead. Yeah, all cats are dead. No, there's no Schrödinger cat in my office. Exactly. Yeah, that's the point. Yeah. So that's maybe a miracle. Yeah, but for large scenarios of our world, yeah, it behaves very classical. Yeah. So quantum effects are small. Yeah. They're classical mechanics, classical theory is an approximation. Maybe it's not the ultimate theory, but it's a almost perfect approximation. Yeah. So that's why we believe, yeah, that the spectra we on the quantum side we have, and you know that if you look at the hydrogen atom, you have this discreteness of spectral values, that they in some sense still approximate and are not completely off, yeah, from the classical spectrum. Yeah, so the associative products, they will be important when we want to understand this process of quantization. Yeah, quantization for me is not just a jump from one world to another with nothing in between. Yeah, if this would be the case, then it would be a kind of hopeless thing to do. Yeah, there would be no point in quantizing classical theories. If classical theories are just plainly wrong, then this is the starting point, which is pointless. Yeah? So we want to take advantage of our knowledge of the classical situation. That's why we want to use that, and we use the associative product. And so the idea is then to replace the pointwise commutative product of the function algebra, C infinity of M, by, well, something which is not completely new, yeah, which is still close to it, yeah, by a deformation of it. And deformation means we are looking for a new product. So if we take two functions, we multiply them now with a new product, and this symbol is the star, that's the star product, just refers to this symbol. So this should be something where we as physicists, I have some dark past as a physicist. So what you would do some perturbation theory. Yeah? You start with a classical theory that was a perfect approximation, almost perfect approximation, and then you add some correction terms. Yeah, so you add some higher orders, and now that's where the Poisson bracket and the H bar comes into the place. Yeah, so you add some H bar terms, and for example, in order to have the commutator here being corresponding to IH bar times the Poisson bracket, you do something like that. You take half of the Poisson bracket of the two functions, and taking the commutator with star will produce IH bar full Poisson bracket. And then you might or might not want to add some additional terms. And why do you need that? These additional terms, they are needed because we want an associative product. Yeah? If you would stop here, this thing would not be associative. Yeah, for associativity. And now things become interesting, because if you say, well, I want to restore associativity in the next order of this small parameter. In natural units, H bar is 1, yeah, but in units adapted to our daily life, in meters, seconds, and kilograms, H bar, the numerical value, is super small. Yeah? So if we want to go one order higher in this parameter, then we need sort of to correct with this next order term the failure of associativity of these first two contributions. But that we can do, yeah. But then we get a new failure in one order higher. Yeah, it's still not associative to the product. So we need to correct in order H bar to 3, and so on and so forth. Yeah. So we need a whole series. Yeah. So if we expand things in H bar, then there will be some coefficients depending on the functions, of course. And we will need all orders of H bar in order to have a chance to restore associativity. Yeah, if we terminate this series for generic functions, this will be not associative. Yeah? And so this is all the problem of deformation quantization, and that we need these infinitely many terms here. Now, of course, the question is, what should this summation here really mean? What should that mean? Yeah, so we need to talk about topologies of convergence and so on. Yeah? And there is one observation. Yeah, one observation is that you see here appears already the Poisson bracket. That's a bidifferential operator of order 1. Each function gets differentiated once. If you continue this game, you see that in order h power to the square, you will need second derivatives of the functions. Yeah? And going on, you see that this CR is typically of order R in each argument.
Excuse me, may I ask a question?
Yes, sure.
Because I'd like to ask about the, let's say, interpretation here, because in the standard veil quantization, we associate the f star g with the function from which the observable for f times g comes from. Do we here still have it somewhere in the background in mind, or is it's purely formal and we do not look at the let's say classical interpretation as observables of Hilbert space?
No, exactly. That's exactly what we want to do. Yeah, that's exactly what we want to do. I will come to this example in a second. Yeah, so this veil quantization, this is precisely of this type. Yeah, and of course it depends all on what class of functions you're interested in. Yeah, but we will see that as an example. Yeah, but let me maybe just finish. Yeah, so what comes out if you look at the formulas, you know, and at all formulas collected over many decades, then this turns out to be a bidifferential operator of order R, at least of order R in each argument. Yeah, and there are, well, you can heuristically argue that this has to be the case. Yeah, depending a bit on the Poisson bracket you have, but this is the typical scenario. So that means that you see more and more of the Taylor information of your smooth functions f and g, the higher you get in this parameter order of h bar. In particular, if you would like this series just to converge pointwise, yeah, for all smooth functions, you would have a problem because of this classical Borel lemma. For any formal series of coefficients, of Taylor coefficients, you find a smooth function which has these Taylor coefficients at a certain point, at your favorite point in phase space. So you always find two bad guys, two functions, such that this series here explodes as badly as you want. Yeah, because you see the whole Taylor information. Yeah, so this already indicates that convergence is tricky. Yeah, and of course this argument relies on the fact that we have here all smooth functions, yeah? and the way out will be to use less functions. But on a generic manifold, well, what kind of classes of functions do you have? Yeah? Inside the smooth functions, and so that's not easy. So this is the question, and there are at least well, there are several options. So the first option is treated as formal power series. In h bar. That's formal deformation quantization. Yeah, and I will give you some proper definitions in a second. Yeah, the other thing is, well, one option to interpret this is to replace the summation by some integral formula, and then you can these integral formulas will then be reasonable or will be possible for certain functions, on certain manifolds M. This doesn't work in general anymore. And then these integral formulas, they allow you to do good and reasonable analysis. Yeah. So then we have a good analysis, and we can have nice topologies involved and so on. So this is in some sense the point of view of Mark Riefel and Klaas Landsman and many others doing that. I will comment on that in a second a bit more. And the other thing is, well, the third option is, well, discuss convergence for, again, certain functions on certain manifolds with respect to some cleverly chosen, let's say, locally convex topologies. Yeah. So, and you see, this is a lot of wishful thinking to achieve this goal. Yeah, it's very vague at the moment. Yeah? But to give you just some idea, so let's discuss this example already here. Yeah? Example, the Weyl product or standard ordered.
And are you interested in distinguishing some values of H bar in which your series converges, or you don't care?
Well, of course, as soon as one discusses convergence, the value, the numerical value of H bar matters. Yeah? Okay. And again, being a physicist by heart, at least partially, I would say, well, the numerical value of H bar is tricky because that depends on your chosen unit system. Yeah. Mm-hmm. In the natural units, H bar by definition is 1. Yeah. Mm-hmm. In my favorite units, H bar is 10,000. In your units of meters, kilograms, and seconds, it's very, very small. Yeah. So this is in some sense, a statement referring to a unit system which is not intrinsic to nature. Yeah. And so from that point of view, you would say, to be on the safe side, yeah, I would like to converge, I would like to have some kind of convergence for all positive H bar. Yeah? Mm-hmm. And then you see this will cause problems maybe, because if you really would have convergence of series, yeah, having convergence for all positive H bar means you have a radius of convergence which is infinite. And so you could plug in all complex H bars, negative ones, purely imaginary ones, whatever you like. Yeah? If this would be the case. Yeah? And then you see that, for example, these integral formulas, yeah? I don't write them down, but there are certain oscillatory integrals, so certain oscillatory phases, and they are very sensitive to whether H bar is real or not, yeah, whether it's imaginary or not. Yeah, if you would plug into these formulas an imaginary H bar, you can get either super nice damping of your integrals, they converge super nicely, or they explode beyond imagination, because H bar then would have sort of the wrong sign, yeah, and you have growing exponentials. Yeah? So this, you cannot expect that, for example, in this second scenario, you really have analyticity in H bar. Yeah? Nobody would ever dream of that, seeing these formulas. It's clear that they will blow up. So the best you can hope for is that these integral formulas, they have let's say, a smooth behavior in H bar at H bar equals 0, but non-analytic. Yeah, that's the generic feature of these formulas here. Yeah, and maybe only smooth from one side, from positive H bars. Yeah, typically they have kind of a reflection symmetry, so it's, as long as H bar is real, it doesn't matter. Yeah, but you're definitely not allowed to plug in imaginary H bars. Yeah, so this will of course blow up. Yeah.
May I ask you a question?
Sure.
Couldn't we consider convergence in some sectors in the complex plane of complex H bar?
Yeah. I mean but yeah. I mean this is what in this third scenario, which I would like to advocate here a little bit. Yeah, this is what happens. Yeah, sometimes you have convergence in the complex plane everywhere. Yeah, or you have to exclude certain points and you have sort of convergence analyticity in the complex plane without certain points. Yeah, this happens, and in the scenarios we have investigated here are very funny, because H bar equals 0 is then typically a boundary point of the domain of holomorphicity. Yeah, so you have sort of singularities accumulating at H bar, but you also have sort of directions where you can take limits H bar to 0. Yeah, and that shows that this convergence features that they will be complicated, and that will strongly depend on the example. Yeah, that will strongly depend on the example. Okay, but maybe I give you one example, at least one example, then that we maybe see what can happen here. Yeah. So the Weil product. So what do? Yeah, you take polynomials in P and Q. Yeah, that's your classical functions, and I consider them to be functions on R2. Yeah, so polynomials, just polynomials, and now what is your favorite quantization? So we take the standard ordered quantization. That's what you see in physics textbooks. So out of your classical observable Q, you assign to it an operator, which I call rho for representation of Q, which is just a multiplication operator. And out of P, you say, well, the momentum operator, that's minus IH bar, the derivative in Q direction, and they act on, well, a pre-Hilbert space. And to make life easy, let's take smooth functions with compact support, for example. Yeah, smoothness, so that I can differentiate as often as I want, and compact support, so that they are L2. Yeah, they are integrable. And now, of course, not all polynomials are linear. You also want higher polynomials. Yeah, so you have now to choose an ordering. Yeah, and standard ordering means that if you have a P to the K, Q to the L, so what do? Well, the standard ordering of this guy would be you first differentiate and then you multiply. So this is first different K times differentiations, and then you multiply. Yeah, so all P's to the right, Q's to the left. That's the standard ordering here. Yeah, and then you get a nice linear map from polynomials to differential operators with polynomial coefficients. Yeah? You can extend this also to arbitrary dependence in the Q variables, as long as it is polynomial in the P variable. So you can, for example, extend this also to polynomial functions on write them like this. So they contain the polynomials in Q and P, but they are not yet all smooth functions on R2. So these are smooth in Q direction and polynomial in P direction. So they are the polynomial functions on the cotangent bundle of the line. Yeah, so that's a geometrically intrinsic way to characterize them. And then we can write the standard ordering of such a function f as follows. So what we need to do is we pick the Taylor information of f in P direction, evaluate at P equals 0, turn these guys into differentiations, and decorate the whole thing. There's a multiplicity factor decorated with H bar over I, and that's the formula here. Yeah. So you see that this formula reproduces on polynomials this prescription here. Yeah, so that well-known formula. Yeah, so that's the standard ordered symbol calculus, if you want. Yeah, that's nothing spectacular, but what you see is that this gives a symbol calculus from polynomial functions on the real line to differential operators on the real line, and that is a linear isomorphism. Yeah, that's a linear bijection. Yeah, it's not, of course, an algebra isomorphism. Yeah, this algebra is non-commutative, the differential operators. These guys here are commutative algebra. But because it's a linear isomorphism, you can define now a star product, a standard ordered star product, just by pulling back the operator product you have here. Yeah? And because it's a linear bijection, this is all well defined, and you get an associative multiplication for this class of functions here. And and that's not yet Weil, yeah, that's standard ordering. And but what you get, and is, if you sort of massage this thing a little bit, you get an explicit formula, and that looks as follows. So so you differentiate here the function in p direction and the other function in q direction only. So it's not very symmetric. Yeah? It sort of splits these two directions. So that's the explicit formula you get out of this construction, and we know it is associative, yeah, because it is isomorphic to the multiplication of differential operators. And it's a nice little exercise to just use this formula I gave you to check whether it's really associative or not. Yeah, so there you have to work a little bit and using Leibniz rules and stuff for derivatives. Yeah, so this is an associative product, and you see you have these infinitely many terms. As long as we have polynomials in the momenta, this guy terminates at some point, and that's why this is only a finite series. But the length of the series depends on the function f, yeah, on the polynomial degree. Yeah, and so the amount of terms is limited by the polynomial degree, but all polynomial degrees can, of course, appear in polynomials. Yeah? So that's why we need infinitely many terms, but we have a nice situation, much nicer than we expected from the beginning. Yeah? Okay, so that's one example, but now you can say, well, this is not the thing we've seen in physics textbooks, so let's compute the failure of being compatible with inner products. Yeah, so I take here phi and psi. Let's say don't care too much about really domains. Let's take a stupid small domain, and I want to compute the formal adjoint of this guy. Yeah? And once you do that, then you see that you have to do integrations by parts. This is all standard textbook knowledge, and then you get the following formula here. We'll need that later. So that with an operator n square, or n, I should call it n. This is the exponential of I h bar over 2. And that's a kind of Laplace operator in an indefinite Laplace operator. So it's this operator here. So you can compute the adjoint of your differential operators explicitly with this formula. And here's a complex conjugation, of course. Yeah. So that's the complex conjugation. So now you see, well, this is not exactly again row standard of f bar. And now you move to Weil ordering. Is just to plug in one copy of n as follows. I mean, this operator is perfectly well defined on polynomials in the momenta in P. Yeah, this series, this exponential series terminates after finitely many contributions. So it's a nice bijection from polynomials to polynomials in the momenta. So now you use this to define the Weil ordering of a polynomial to be the standard ordering of NF. Yeah, you can also write down a formula for that. And this yields then again a bijection because n is bijective, rho was bijective, and then we can cook up a Weil product. And this is really the the Weil product for functions which are polynomial in the momenta and smooth in the position variables. Yeah, and there you have also formulas for it and so on. And okay, so that's an example, and this formula already shows sort of a lot of the pain we will have here when going to deformation to convergence. Yeah? Okay, so now I should conclude a little bit the history here of the process. We have very strong classification and existence results for formal star products. So let me give you the definition here of a formal.
Stefan, just a quick sanity check. So if your F is real, then this Q Weil of F is self-adjoint, right?
Yes. Well, it's symmetric. Let's say symmetric.
Yeah.
I have not talked about proper domains,
yes.
but it's a symmetric operator.
Symmetric, yes.
Yeah. So this, okay, let's add this here. So this guy, if I take sort of the formal adjoint, this is the one corresponding to
exactly.
Yeah. And on the side of the product, that simply means that complex conjugation, which is the classical star involution, is a star involution for the Weil product. Yeah.
Yes.
That's the feature we have. Yeah. The two features which are of course not independent. Yeah. We have. And you see here in this version, we can speak about that without talking about domains and things like that. Yeah. Here this is really the formal adjoint coming from integration by parts on the domain, let's say, non-problematic domain. Yeah. So I don't want to talk about domain issues.
Sure.
Yeah. So this is the algebraic feature I'm interested in. Okay. So the general definition, so this is Poisson manifold. And then formal star product is an associative now formal power series in H bar bilinear multiplication, which I write as F star G being sum of guys I expanded in powers of H bar with so should be associative bilinear over the formal power series ring and with the following features. So first of all, in lowest order of H bar, it should be just multiplication. In first order of the commutator, I should get the Poisson bracket, or I times the Poisson bracket. And then one can add something like that the constant function 1 should behave as unit. It is not very harmful to require that these guys are bidifferential operators. This is not motivated by physical means, but all known constructions essentially turn out to be of that type. Yeah? So you can make it part of the definition or not. This is the matter of choice. And you might want a fifth one that the complex conjugation is an involution where, of course, I have to say how to treat H bar, yeah, for real H bar. I want this is then also sometimes referred to as a Hermitian star product. Yeah? So the standard ordered star product does not fulfill this feature, but the Weil product does. Okay, so that's the definition of a formal star product, and that goes back to Bayern, Flato, Fronstal, Lichnerovich, Sternheimer in the 70s. And now we have a lot of nice results, existence and classification. So there are many names involved, yeah, and first people looked at the symplectic situation where the Poisson bracket is non-degenerate, and there De Wild and Leconte gave the first existence proof in 83. So 83, that was Leconte. then there was a very beautiful construction of Fedosov in the symplectic situation of star products based on geometric data. So you just have to invest a covariant derivative. And then, of course, there was this famous paper of Kontsevich settling the existence and also the classification in the complete general case of Poisson. And I should also mention that we have in the so this is symplectic existence. This is Poisson existence and classification. And there were also in the 90s, there were a classification of the symplectic situation. Then one can be much more precise or detailed than in the general Kontsevich situation. There was Richard is here, right? Yes, he's here. So Richard and Boris Zigan and Melanie Bertelson, Michel Cahen and Simon Güth. And well, there were a lot of groups doing this classification in one or the other way. Deling was involved, and so there are several approaches to what we now call the characteristic class of a star product, of a symplectic star product, which is a specific way to construct a cohomology class in the second de Rham cohomology, formal power series. Okay, so let me just stop here. There are many more results on symmetric star products under certain group actions. One can discuss representation theory. One can understand the Morita equivalence and whatnot. Yeah. Phase space reduction and all these kind of nice results, but
sorry, I have a question. While mentioning this characteristic class, you mentioned that this class is in the second cohomology, or is it in the third one?
No, the classification of formal star product happens in the second de Rham cohomology of the manifold. It's a formal power series of two forms, of closed two forms, classes of them.
Maybe the abstraction for existence of a star product lives in third cohomology.
That would be the kind of naive Hochschild cohomological recursive obstruction that would be the third Hochschild cohomology. And this is known to be non-trivial, right? I mean, the Hochschild cohomology is super big for a manifold. Yeah, and so in principle there are obstructions. There's the possibility for obstructions. But this obstruction theory, that doesn't tell you to solve the problem. That only tells you, well, you might have a problem. Yeah. And the existence theorems, they tell you, well, actually you don't. Yeah. You can circumvent the obstruction by clever choices. Yeah. But the third Hochschild cohomology, that's a huge infinite dimensional space for a manifold, for the functions on the manifold. That's anti-symmetric three tensor fields, three vector fields. Yeah, so it's a big space, yeah, infinite dimensional space, unless your manifold is two-dimensional or lower. Yeah, then so in principle you have obstructions. Yeah, if you want to build up your star product recursively. Yeah, but nobody tells you whether these obstructions really strike or not. Yeah, and the existence proofs show you that you can make clever choices so that they don't kill your process of constructing things. Yeah. So
thank you. I see.
Yeah. Okay. Well, okay. So that's the story. And the big but is this is only formal power series. Yeah. So that's the really bad luck if we want to cook up some interesting topological algebras. Yeah, so no C-star algebras inside at the moment. Yeah. Now let me come back to the 2 points I mentioned here already. The integral formulas. Let me elaborate a little bit more on that. What can be done? Yeah. So need some more space. Yeah. So convergence by integrals. Yeah. So that's of course a long story, and I'm definitely not the expert to do so. You have to ask Mark or some other people here in the audience. They know these kind of things much better than I do. So the idea, or one way to approach this is you do not start with polynomials in the momenta, yeah, because they lead to these very singular operators on the L2 space, to these differential operators. But you start with nicer symbols, let's say in the quartz space or something like that. And then you use integral formulas instead of, and view them as integral kernels. Yeah? And then you get composition laws, which are corresponding always to certain bounded or even very, very nice trace class operators. Yeah? And you can also pull back their operator product to the nicer symbols than these polynomially growing ones. Yeah? And then by means of integral formulas. Yeah? So you have integral formulas for compositions of, well, they're pseudo differential operators, yeah, but very nice ones, yeah. So that they really form an algebra and very nice ones, yeah. So very nice ones, and that was known. In some sense, you find the formulas in Hermann Weyl's book, yeah. But the analysis was of course, you have to elaborate a little bit more. And the idea of Mark Riefel is that that what is actually going on here is that you have an action of R 2n on this R to n by translations. I mean, it's a group, yeah. And there's a question?
No, I don't think so. No.
No, okay, fine. Yeah, please ask. Yeah, and you use this to get an action on spaces of functions, of course, first of all, yeah, on functions, and then after specifying the nice classes of functions, you can use integral formulas directly using this action. And that sort of opened the door to many constructions, because once you realize this, then you can transfer this to actions of, again, the group R2n, the symplectic form, on, well, all kind of algebras. It don't need to be functions. Yeah, so in particular on C-star algebras, but also some locally convex algebras and whatnot. Yeah, and you can find new products for such algebras out of the old ones. Yeah, and that's kind of the idea of Mark Riefel to cook up convergence, and there, I mean, h bar is a number, right? I mean, h bar is any real number, and this works. Yeah? So, and you have a nice analytic framework. You can cook up nice topologies for which these new products are automatically continuous. And you typically start with a locally convex product, and then it requires, under certain conditions to be fulfilled, it requires a little bit more effort to actually cook up some C-star norms also. Yeah, and then you can complete, and you get out of old C-star algebras with such an action, you get new C-star algebras now being deformed. So that is in the Rieffel's work in the 80s, I think. Yeah, so please correct me. Yeah, that's and then of course one can wonder, well, actions of this abelian group, they are very nice, but maybe there are others. Yeah, there are other groups acting, and with integral formulas sort of the same kind of flavor. Yeah, and so one has some more general groups, and that is done by Pierre Bieliavsky. And Victor Gerard, and maybe more persons. So that's the 2000s and something like that. Yeah. So there are certain other Lie groups, if they act in a specific way, then you can sort of mimic these constructions also for those. Yeah, and you can deform algebras in a nice analytic context. Yeah, but you see, you need groups involved, you need actions, and now the question is whether you have interesting actions producing all Poisson brackets, but this is easy to see. Will not be the case. Yeah, so this is they are examples. Yeah, but these examples, unfortunately, by far do not exhaust all interesting Poisson structures. Yeah? So they do not. Unfortunately, yeah, that would be too nice. Yeah, and so the idea, what I would like to advocate now is a bit, again, only looking at examples. Yeah? I mean, I cannot do more than that. Yeah, but to advocate for some more direct approach, yeah, by looking at this convergence of the series directly, and so this is the maybe the second section. So the program. Oh, excuse me. Okay, much here. Okay. So now, what's our idea here? And this is now done by my group for many years. So it sort of started around about 10 years ago, and involved many people working on that. So that is Chiara is here. Yeah. Yeah, there was a student of ours. It's Matthias Schütz, who is in Warsaw at the moment. Well, at least as his position is in Warsaw at the moment. There's Philipp Schmidt, and many more. There's Michael Heinz and Oliver Roth, and many more. Yeah. So this sort of involves now a long list of people. Yeah. And so the idea is, in some sense, well, we start with the functions here with formal star product. You know? Okay, we know this always exists, and but that doesn't really help. And now the first step is we need to identify subalgebra of the formal power series, subalgebra with respect to this star product, such that we have trivial convergence. Okay, I will not give you a definition of what trivial convergence means. This is you understand it when you see. So what do I mean by that? Going back to our example here, yeah, with this star product. If you take a look at this star product, you see, well, if, for example, the functions consist of polynomials in P and Q, then this series will terminate at a level depending, of course, on the polynomial degree. So we have trivially a convergent product for all H bar. So no difficulty here, as long as we work with polynomials. This will be an example. And so hope is, and this is really, let's put this here, this is just a hope. In green, because it's a hope. This is not at all guaranteed that you can find something like that. This is bound to work in some examples, and that's it. Nothing more, unfortunately. Okay, so I want to be honest. So this is the program fails in the first step. Nevertheless, maybe sometimes you have luck enough to pass this first step. You see in examples, it is not completely uncommon. This formal deformation quantization business has two aspects. You have these very, very general existence and classification theorems, where you have existence proofs which do not really give you interesting features. So you cannot control the outcome. It is just a formal deformation quantization, full stop. And then in examples, where you understand your phase space in detail, where you have interesting geometry around, where you have symmetry groups, where you simply know more things, you can typically cook up very, very, very specific examples of star products, not relying on these general existence theorems. And for those, like for our standard order product, this is not completely absurd to hope for something like that. So this is really a program which might work in interesting examples, and where I do not have much hope of gaining very general existence theorems. This is too much. I think the convergence, this will depend on specific information, on examples. So the second step is once.
So sorry, regarding these examples, so typically these manifolds should somehow be very symmetric, or?
I think all of our examples are, but I think it's not, let's say it that way, the symmetries help to understand the situation. They give you a good hint what kind of algebra of functions you should look at. If you have no symmetries whatsoever, I don't know. I mean, all our examples at the moment are of that type. Yes.
So in particular, these examples, all of them involve Lie groups, or? Yes.
There are manifolds with large Lie groups acting on them. So it's and also of course in a nice way compatible with the Poisson brackets and so on and so forth. So I will give you some more examples than just the one we had of the polynomials and on the vector space. There, in some sense, the group is the vector space acting by translations on itself, and then the polynomials, they are representative functions. They have finite orbit under the group action. So that's why they are specific for this vector space situation. But we have other examples not related to vector spaces directly.
Okay, thank you.
Okay, so but still, this is sort of wishful thinking. This is just a hope. You might do that in examples. Okay, and then the second is identify typically locally convex topology on A, such that, well, the star product is continuous. And, well, again, I should switch colors. This is just hope, unfortunately. So this is not really clear whether you can always achieve that, under what conditions you can always achieve this. We have examples where it works, and finding this topology is typically, well, a mixture of experience and pure guessing. And so you start with pure guessing, and then you find more and more examples, and then you start to see patterns. But I would say we are still very, very far from having a general feature. Why do I insist on locally convex? Well, the nature of the problem is that you are talking about something like canonical commutation relations. So we expect something like CCRs, and therefore we have no submultiplicative seminorms. Of course, 0 is always a submultiplicative seminorm, but no non-trivial ones. Yeah, as soon as we have canonical commutation relations in the game, like for example in the while product, the commutator of P and Q is a multiple of the identity, then you know that there cannot be any non-trivial submultiplicative seminorm. Yeah, so that's bad luck, because locally convex algebras built with submultiplicative seminorms, there's a lot of literature, there's a lot of technology available. These are kind of one way to view them is projective limits of Banach algebras or normed algebras. So there's a lot of technology available. Yeah? This is all not available in our situation, unfortunately. Yeah, so there's no hope that one gets anything out of that theory of locally multiplicatively convex algebra. So the best thing we can have is to have seminorms where the seminorm of a product can be estimated by a different seminorm of the factors. You know? And that means that you will require, you will need already a countable amount of seminorms, at least, maybe even more than that. Yeah, so you can hope for countably many, and again, finding them, this is part of the game. Yeah. Now we come to good news. That's easy. Yeah, complete. That's always easy because we have a continuous product. Nice topology we can of course complete, and then we get a complete locally convex algebra, and locally convex algebra A, let's say, completed, and we can start studying this A hat. Yeah, so that's then we are hopeful. Hopefully we have interesting algebras. And of course, the game is to make it interesting. Why do I sort of split this into these steps? The idea is that the algebra you start with here, which you hope to find something like the polynomials, that's small subalgebra. Yeah, that's so this is typically small and easy to handle, easy to find, and you hope, yeah, that you have a locally convex topology, which is in some sense very coarse, so that the completion should be large, should contain interesting elements, not just polynomial functions, but more interesting things. Okay, so that is in some sense. There's a question?
No. I like the idea. So the completion will preserve the properties you're after. Yeah. The convergence, yeah.
Of course, yeah. I mean, that's then part of the step 4, and this is in some sense standard. You can now, I mean, once you have a nice locally convex algebra, you can ask all kind of questions, and you can hope to answer them. Yeah, that's a then kind of canonical questions you would like to see. Yeah, so what are the positive functionals on them? Do they have representations by not too wild operators on Hilbert spaces, and all these kind of questions you can ask once you have the algebra. Yeah, and of course, getting the algebra is the complicated thing. Yeah, then the step 4 can be very complicated as well, but that is sort of, you have a lot of kind of standard techniques to attack this problem. Yeah, and unfortunately, step 1 and 2 is yeah. I can present you now examples. So that's, I think, the third part.
May I ask you a question?
Yes, there are many questions. Sorry.
I have a question. If you consider positivity, you would need some star structure.
Yeah. Okay.
What do you assume about compatibility between the star structure and this? all this.
That's true. I didn't mention that. Yeah. So if we scroll back a little bit, so this is, well, of course, first of all, you need something like that. Yeah. I mean, you want to start already on the formal level with a complex conjugation as star involution. That's no problem. Yeah. So this is sort of easy to achieve. Yeah, on the formal level. And it turns out, yeah, that the difficult part in step 1 is the product and not the involution. Yeah. So the involution typically is sort of easily continuous. Yeah. That is I mean, this is in examples, right? I mean, there's no general theorem, but if you think of it, yeah, this is to be expected. An involution is an anti-linear map, but it's linear map. Yeah, it's just but a product is a bilinear map, and the continuity of bilinear things is much worse. Yeah, that's much more complicated to control. Yeah. So I didn't mention that here. Yeah. So because that is kind of the easy part. Yeah. To have the star involution, the complex conjugation being continuous, that's kind of, well, almost automatic. But of course, if you want to talk about positivity, you need some kind of involution. That's true.
So sorry, related to that comment, I expect that the separate continuity, the continuity of the product with respect to each variable, but not jointly continuous, is not enough. Yes.
No, that's not enough, because then it doesn't pass to the completion in general. Yeah. There's no reason why it should. Yeah. I mean, this is then you would get on the completion. You would only you get some kind of partially defined multiplications. Yeah, that's the problem. I mean, I require a lot. That's true. Yeah? I mean, we know that many interesting algebras, they only have separate continuous products. Yeah, so these are excluded in my scenario. Yeah, that's a choice. But the advantage is that that then completion is sort of automatic. Yeah, that this is then easy, but of course the price is that we have maybe a fairly restrictive scenario. That's true. Yeah?
I see. Okay.
I mean, you have, of course, general statements that if your locally convex space is not too bad, then separately continuous bilinear maps are automatically honestly continuous. Yeah, jointly continuous. You say jointly continuous is the right one. Yeah, I mean, they are continuous. Yeah, so there are scenarios in kind of countably many seminorms and things like that. Yeah, you get completions to Fréchet algebras, but in general, this is not the case, and it might or might not be true. Yeah?
I see.
Okay.
Thank you.
But yeah. Yeah, this is, I mean, very different from the world of C-star algebras, right? There you only have one norm to take care of, and that's all nice. Yeah? But this is, we are still very far away from C-star algebras. But now I should give you an example. Yeah, now at least one example. So we start with a vector space. Let's say real or complex, doesn't matter. And then we take the symmetric algebra. And we think of that can be viewed as being part of the polynomial functions on the dual. Yeah, and depending when V is infinite dimensional, then it will be only a very tiny part, and then it will also be a question what dual I really mean. If it's finite dimensional, then the symmetric algebra is the same thing as the polynomials on the dual. Yeah? So this V star will be sort of the phase space. Yeah? And now let's add here locally convex vector space. For example, a finite dimensional vector space, or any interesting locally convex space you have encountered. If you want to do infinite dimensional systems, there are good reasons to take some test function spaces here or so. So then symmetric algebra. Now the idea is that we take a bilinear map. Let's call this little pi from V to the real numbers or complex numbers, bilinear, it doesn't matter too much. And it should be continuous. Yeah, so that means that because it's the target are just the scalars, that simply means that there exists a continuous semi-norm little p, such that if I take pi of these two vectors and take the absolute value, then I can estimate it like that. Yeah, this is the continuity of a bilinear form. Now we cook up the Weil product corresponding to that, and so for that reason we first need an operator p pi that goes from the symmetric algebra, two copies of the symmetric algebra into two copies of the symmetric algebra, lowering the degree of the polynomials by one in each argument. And so let me just, so these are polysymmetric products of vectors in V. And you have a different amount here. And the operator will be defined as follows. So what you do is you plug in one of the V's and one of the W's, and you keep the others. So the ith one is missing here. The J one is missing there, and you sum over I and J. So that's an extent linearly. That's the operator we have, and it turns out that what you do now is for F and G being elements in the symmetric algebra over V, we get a new product which I call star product depending on pi. So what we do is we take the symmetric product and we exponentiate this operator p. Yeah, so with your, let's say, IH bar over 2 if you want, just to and apply this operator here. So this means that these F and G, they are kind of sums of expressions like that, symmetric tensor products here, and we pair them all factors like that more and more often. All powers of p enter in this exponential series, and you see that this exponential series is in fact a summation, because this operator lowers the degree, and at some point no vectors are left. Yeah? So this determines, and this is the usual symmetric tensor product. And so if you and this is associative. Yeah, and as an example, what we can do is we can take two-dimensional vector space, and we have coordinates q and p, and then this pi we take as the pairing so we have two coordinates q and p, so we have q p and q prime p prime, and if I remember correctly, it will be q, no, it will be sorry, p q prime. It will be this bilinear form, and if you do this whole machinery, then you get this formula. So this will be IH bar over 2. Maybe this was a not so clever idea to use this normalization. Let's take it the other way around. So it's p q prime minus q p prime, and then this operator here yields exactly the Weil product. I hope I got the three factors right. Yeah. So our Weil product and the standard ordered product and all these, they are particular cases of this construction. You see, this works in infinite dimensions and blah blah. And in finite dimension, this continuity is automatic. That's trivially fulfilled. In infinite dimensions, it becomes a condition. And okay, so yes. So this construction is nice. It's always associative, and now we have found our kind of our first step, right? This is an algebra where everything trivially converges. There are finite summations. Okay, and so we have to move to the second step. Yeah, and this, well, the interpretation is, of course, that these guys here, they stand for certain functions, yeah, inside these polynomials here, inside the smooth functions on the dual. Yeah, forget about the dual. Yeah, nobody likes duals. Yeah, so this we don't do. And well, now find the topology. Yeah. Yeah, that's the question. Yeah, to make this thing continuous. And one way to do that is so we choose a parameter R, real parameter, which sort of is used to control the growth. Yeah, and now we want to control here this convergence. Well, we have to compare polynomials of different degrees in a coherent way, in a systematic way. And how do we do that? Well, if we have a continuous seminorm on V, well, what we get, of course, continuous, we get seminorms on tensor products. Yeah. And therefore also on the symmetric tensors. And here they are inside here. Yeah. So we take this tensor powers of this seminorm. Yeah. So they would define the projective topology here. These seminorms, the collection of all those seminorms. And now we have sort of a nice way of extending, of cooking up a topology for all symmetric powers. But not for the symmetric algebra. That's a direct sum. Yeah, but so the question is, what do we do here on the direct sum of all those? Yeah? And each of them is equipped with a projective topology, but the direct sum, well, there we have many options actually. Yeah, there's we can take the Cartesian product topology. That's very coarse. Yeah, that would correspond to something like formal series. Instead of polynomials, we can take the direct sum, the locally convex direct sum topology. Then this guy is already complete. Then there's no way to complete to something interesting. That's too fine to be interesting. Yeah, or we do something in between. Yeah, and so we have to relate different tensor degrees. Now, what we do is the following: if we have an element in here, in the symmetric algebra, yeah, where these guys here are elements in Sn of V, yeah. So it's a finite sum. I just don't want to specify the upper limit. Yeah? It's finitely many terms. It's in the symmetric algebra. Then I would like to define a new seminorm for those guys by taking the nth tensor power of P of the components. Yeah? And now, well, I have to do that for all n somehow. Yeah? And one way to go is I just sum over all these things. And then I want to bring into the game this parameter. Yeah? This is the parameter which we want to choose. Yeah? And so we want to sort of have a growth condition on the, you can call these things the Taylor coefficients if you want. Yeah, and so let's do the following. N factorial to the power r. Okay, this is magic. Yeah, that's why this turns out to be a clever choice. Yeah, okay, it turns out to be. Yeah, and then you have the following theorem. Once you made this choice here, the actual proof of the theorem is not that bad. Yeah, I mean, this is kind of a going through estimates. Yeah, but the theorem is this star is continuous with respect to locally convex topology generated by all those seminorms, P is a continuous seminorm on V. I fix the parameter R, so this is fixed once and for all, and I take all those seminorms here on the symmetric algebra, and then this guy turns out to be continuous. Yeah, and a nice little exercise to actually prove that. I won't do that here, but it's once you have this idea that this might be good, that's true. For R at least 1/2. That's I should know.
Okay.
Yeah, it's not for all R. Yeah, it's this is the crucial point. Yeah, and and you see that the bigger R gets, the more restrictive are the conditions, so the completion becomes smaller. Yeah, the coarsest topology is for R equal 1/2. Yeah, there you get the biggest completion, and it's nice because, for example, exponentials of vectors in V, yeah, in the sort of formal exponentials, they're not in the symmetric algebra, but they will become elements of the completion if R is less than 1. Yeah, for example, if R is equal 1/2. Yeah, we have exponentials in there, and then we get back to the kind of canonical commutation relation in their exponentiated form. Yeah, so they will be part of this example. Yeah, and you can study this example. The star involution is continuous. That's almost trivial, and you have positive functionals. So if R is positive, in particular for 1/2, then the evaluation functionals build out of elements in the continuous dual. Yeah, so if I view them as functions on the continuous duals, I can evaluate at points. These evaluation functionals, they turn out to be continuous. So the completion really still can be viewed as functions on the continuous dual. And there are certain functions you can describe by many means. Yeah, so that you can relate that, at least in finite dimensional situations, to known functional spaces.
Thomas?
Question?
Yeah.
I have a question. Why 1/2? Could you give us a hint?
Okay, so there's a little heuristics. I mean, it turns out to be the optimal choice among these parameters. Yeah, so there might be other topologies of completely different nature I don't know of. Yeah, but how can you argue? Well, this PR, this operator P here in the exponent, that is something like differentiate once F and once G. And you exponentiate this operator. So if F and G are polynomials of a certain degree n, yeah, then exponentiating this operator will differentiate n times in particular, also less, but n times occurs, producing an n factorial for each of the factors. Yeah? You divide by 1 n factorial because of the exponential series. But that leaves you an n factorial sort of in the denominator, which might be problematic for convergence. So what you have to require is that the Taylor coefficients of the functions, they overcompensate this n factorial in order to get convergence. Yeah, because there are 2 of them, they can conspire and they can share who is overcompensating what, but together they have to overcompensate an n factorial. And in some sense, these seminorms, they are very symmetric. Yeah, so it's fair if they share the problem. Yeah, and that's the 1/2. Okay. I mean, it's a heuristics. Yeah, I mean, in the end, you have to do the estimates. Yeah, and then you see that it works. Yeah? But that's the way I sort of explain things, if you want. Yeah, so that this you have to overcompensate an n factorial coming from the formula of the star product.
So maybe I also have a question related to that. So
sure.
This somehow explains why 1/2 appears in this formula, but still somehow I'm surprised that 1/2, this is still continuous. So you have weak inequality, yes?
Yeah, but
I would rather expect that it would be continuous for R strictly bigger than.
Very good question. The point is I'm using all seminorms. Yeah? I'm using all seminorms. And in particular with P, also constant times P is a continuous seminorm. And so note, it's a good question. If P is a continuous seminorm, and so is C times P for any constant, right? But that means that in our formula here, we have to take the tensor powers of this guy, and that is really the exponent C to the n times this one. Yeah? And so that means that automatically we can sort of absorb exponential growth in n, yeah, because we can scale, we can just pass to a different seminorm by scaling the seminorm we had, and then this allows us to absorb exponential growth, and that's why R equals 1/2 still works. You need this trick, yeah. You need to sort of multiply you have to scale your seminorm by 2 at some point in the proof or so, yeah. So this is why it works, yeah. It's not, this topology is not built out of a single seminorm P, yeah. Then you would have indeed a problem, yeah. But for all of them, and even if you start with a normed space, you have to take all multiples of the norm as well, yeah. So it's so this topology is not normable, yeah. Definitely not. Yeah, it really, because these seminorms here, yeah, you cannot estimate this seminorm by this one anymore. Yeah, this is really strictly bigger. Yeah, so for C bigger than 1. Yeah, so this is, they are not comparable anymore. Yeah, while of course P and C times P, they are comparable seminorms. Yeah, by the very definition. Yeah? So this is lost, and this trick is really needed and crucial for the proof. Yeah, that's important. And so it also shows that this is an intrinsic topology. It really depends only on the locally convex topology of V and not on the choice of seminorms or so. Yeah, because we take all of them. Yeah, I mean that's if you want to make things independent of choices, just take all. Yeah, that's the idea. Okay.
So can you remind me whether V is a complex or real vector space?
It doesn't really matter too much. Yeah? I mean, you can, I mean, in examples, you would probably start with a real vector space, but you would allow your bilinear form also to take complex values if you want. The continuity is very robust. Yeah, so you can also, if you plug in here, a different complex number would still go through. Yeah, so this. Maybe I should tell that this is then the map taking the H bar to F star, and now I write really the H bar here. This is empire. So that's a map from all complex values, and this is in all in the completion, and for all F and G in the completion. Yeah, as long as they are only polynomials, it's polynomial. That's not a big deal, but it is an entire function with values in this completion. Yeah, so you can play a little bit around there and get all the interesting examples which are sort of corresponding to constant Poisson brackets into the game. Okay, but you want to see some more interesting examples, I guess. Yeah, that and I'm running out of time here. Anyway, let me just be a bit more fast now. More examples. And in some sense, they are all building on this example. So that's why this is the important example. Yeah, this topology here on the symmetric algebra, let's call this the S index R topology. Yeah, that plays a role in all the other examples. So, for example, what I particularly like is the following. You start with a Lie algebra. And assume that this is with a Lie bracket is not only continuous, but even, well, the analog of submultiplicative seminorms, right? So we have a system of seminorms such that we can estimate here the Lie bracket with the same seminorm here. Yeah? So system of seminorms with this property. Yeah, and we would probably call a locally multiplicatively convex Lie algebra. So any finite dimension Lie algebra has that feature for free. Yeah, so that's only a condition if you go to infinite dimensions. Yeah? But then if you take, for example, the Lie algebra corresponding to a normed algebra and commutators, then this is the case. Yeah, so and then what you do, you take the symmetric algebra over that, and you know that this is there's a nice vector space isomorphism to the universal enveloping algebra. Yeah? This Poincaré Birkhoff-Witt isomorphism, yeah, of total symmetrization. So which sort of I mean the easiest way is to say that if you have a symmetric power, then it is mapped to the power in the corresponding power in the universal enveloping algebra, and by polarization you get the Poincaré-Birkhoff-Witt isomorphism. So because it's a linear isomorphism, you do the same thing as before. You take the product you have on the universal enveloping algebra and pull it back with this sigma. Yeah? So you define for x and y in here. You define this thing here and sigma of it, and now this would be a product isomorphic to the universal enveloping algebra. And now you can also smuggle in a little bit of H bars to have this difficulty here. So I modify this isomorphism by smuggling in some H bars here, or I take here the rescaled Lie bracket, yeah, by a multiple of H bar. And
I hope that you take a quantum group in.
Yeah, but yeah, it's not yet a quantum group. It is the universal enveloping algebra. This is not default. Yeah, it's just scaled. Yeah, it's just a different Lie algebra if you want. Yeah, so it's really rescaled and not really. It's still co-commutative.
Yep.
Okay. Yeah. So this guy is a isomorphism of co-algebras, and it's co-commutative. Yeah. So it's not yet quantum group. Yeah. That's another story I have no idea about. Would be fun, yeah, to understand that. Yeah. So anyway, and this is called sometimes the good star product, and I think Drinfeld also used this in 83. So it's equally well called Drinfeld star product. People call it the Poincaré-Birkhoff-Witt star product, or the because the formula involves the Baker-Campbell-Hausdorff series, they call it the Baker-Campbell-Hausdorff star product. So it is the star product corresponding to good Drinfeld, Poincaré-Birkhoff-Witt, Baker-Campbell-Hausdorff. Yeah? So,
oh my goodness!
And I don't want to write that, so it's just the star product. Yeah. And now, now the theorem here, under this condition that our Lie bracket has reasonable continuity properties. You see that this guy here is continuous in the SR topology for, well, 1. We need R at least equal to 1. Yeah? And so in some sense, so this is a theorem with Chiara Esposito and Paul Stapor we had some years ago. And the change that we have to enlarge the parameter is the reason can be seen that if you look at a certain power of H bar of this product, it involves Baker-Campbell-Hausdorff terms, many of them. Yeah, and the problem with Baker-Campbell-Hausdorff is that it has so many terms. Yeah, and has so many terms that you are, in some sense, compared to the previous situation where you have this constant Poisson structure, here in this case of the linear Poisson structure, you have to it's not about the growth, the size of the coefficients, they can be estimated, but the number of terms is simply much bigger, and that requires a more restrictive convergence scheme. Nevertheless, you have here continuity, and I think this is a funny result because it gives you a way to turn the universal enveloping algebra into a locally convex algebra, and you can complete it, yeah, with a continuous product. Yeah? So it might even be useful to do Lie theory. Yeah, so that's an example which we found here with Chiara Esposito for myself some years ago. And maybe the last one I want to discuss, and that is just to convince you that we are not only dealing about vector spaces. I mean, here the underlying space is there are still functions on the dual, but the dual is a vector space. Yeah, so you want to go to more interesting topology. Yeah, so more interesting geometries. And what you do is to, excuse me, what you do is you take a Lie group and you take its cotangent bundle. You know, that's any cotangent bundle has a canonical Poisson bracket, and this is a particularly nice one because you have a lot of symmetry coming from the Lie group. Yeah, so the point transformations, they are all of the left multiplications, they leave invariant the Poisson structure. So you have a nice symmetric situation. Yeah, so this is with canonical Poisson bracket, and now we have to cook up a star product for this. And the point is, in general, what you can use is a covariant derivative to cook up star products. And if you look back, I hope I find this here now, for our standard ordered quantization. Yeah? If you look long enough, a PhD long enough, for example, at this formula, then you see that you should interpret these partial derivatives as covariant derivatives. Well, some people might get this idea quicker than I did, yeah. But and then you can sort of take out of a covariant derivative, you can cook up on any cotangent bundle of polynomial functions. You can have an isomorphism to differential operators. You can pull back the operator product. You get a star product on any cotangent bundle. Once you have specified a covariant derivative, this is kind of implicit in this example, and you can do that in general. Yeah? So use covariant derivative on G to get a symbol calculus, and that means again a standard ordered, if you want, from polynomial functions on the Lie group cotangent bundle into differential operators on G. Yeah, and now this you can do for any cotangent bundle, and that's nice, and that gives a kind of a star product here by pulling back things. So that's a linear isomorphism again. Gives you a star product here on any cotangent bundle where this is a subalgebra and it converges trivially. Yeah, so our first step in the program is done. That's the good news. Yeah, for any cotangent bundle even. So that's nice. And now the point is, on a Lie group, we have, of course, a very nice one, and that's this famous half commutator connection. Yeah, so that means if you take a left invariant vector field for psi and eta in the Lie algebra, these are the left invariant vector fields. You take as covariant derivative the left invariant vector field corresponding to half of the Lie bracket of them. Yeah. And that extends to a covariant derivative, torsion free. That's why we choose here 1/2. Yeah, that's a classical fact. That's nothing new. Yeah, so the little exercise in differential geometry. And the nice thing is this only involves Lie theoretic data. We have not made a choice actually. Yeah? So this is completely canonical. So we have a completely canonical symbol calculus on a cotangent for a Lie group, yeah? Based on this half commutator connection. And so now the difficulty is, well, what is the polynomial functions on the Lie group and the cotangent bundle of the Lie group that can of course be trivialized into the Lie group and the dual of the Lie algebra. And so the polynomial functions, they can actually be written as functions, smooth functions on the position variables, that's the Lie group, and this is an honest tensor product, the polynomials on the dual of the Lie algebra. Aha, that's very nice because this here is just the symmetric algebra over Lie algebra. And here we know already what to do. So the point is that this star product you get here, and this is the real good star product if you want, that kind of restricts to the polynomial functions here, which are just the polynomial functions on T star G, which are G invariant, where this prefactor here is constant. Yeah? And then yields our famous Güth-Drinfeld, Birkhoff, Witt, Baker-Campbell-Hausdorff star product. So here we know on this tensor factor, we know what to do. Yeah? The question is what to do in the other tensor factor. Yeah? And we also know that because we have differential operators, we need to restrict the class of functions here. Yeah? So on the S dot G factor, we take the SR at least one topology. That's nice.
Tomek, you want to ask a question?
There's a question, right?
Yes. If you are taking G invariance, you are assuming that the action of G on this symmetric power of the Lie algebra is trivial.
Yes, that's I mean, this depends on, it's not the adjoint action here. Yeah, if you take here the, oh my God, left or right trivialization, you can arrange things in such a way that the lifted action of G on the cotangent bundle produces an action on the polynomial function such that here you have left translations and here you have the trivial action. Yes. If you would use then the other trivialization, you would get here an adjoint action as well.
Does these two choices lead to the same quantization deformation?
Well, this is the useful isomorphism. Yeah, I mean, this is I mean, I'm choosing this trivialization in such a way that I can factor things in such a way that here I have a complicated action. Well, complicated, it's by left translations, yeah. And here I have no action at all. That's a trivial action, because then I can of course, I also have a adjoint action here, but that would correspond then to right translation and not to left translations. I mean, I just want to make to motivate that this tensor factor here is really as a star product subalgebra available, and corresponds to the G invariant guys, and the star product I'm constructing with this connection is G invariant because I have only used Lie theoretic data. I mean, there's a story behind. I mean, you have to believe me this. Yeah, there are some computations to be done. Yeah, this is not on the nose. Yeah, I mean, you have to work for that. Yeah, this is not completely. You have to prove that. Yeah, I mean, this is what comes out after a couple of computations.
I have a linguistic doubt about this procedure, because you could think about star products up to gauge equivalence.
Yeah, yeah.
And this different choice of trivialization of the cotangent bundle to the group, somehow they are related by some gauge trick. So I wonder if one gauge trick would produce a gauge equivalence between star products. But maybe
I mean, well, we also have here a while ordering. Yeah, I mean, you can also do that on general cotangent bundles. Yeah, and they are related by a similar operator as before. Yeah, this operator n, you remember. Yeah, so there's a and first, I mean, this is a choice. Yeah, I mean, corresponds to a choice of an ordering prescription. Yeah, I mean, this standard ordering or while ordering or whatever kind of ordering you might be interested in. Yeah, the standard ordering is not a clever choice for many reasons, but it's a very simple one. Yeah, and you are maybe more interested in while ordering. Yeah, because there you have the star evolution. Yeah, which is nice. Yeah, and the point is concerning the continuity. What we do is we prove the continuity for the standard ordering, and then we prove the continuity of this operator relating standard to while ordering. And that is much easier because this is a linear map, and continuity of linear maps is easier to control than continuity of bilinear maps. Yeah, and for the I mean, we could have started with a while ordering directly and proven continuity sort of directly, but that's much more cumbersome. The formulas are much more complicated, and you need for estimates you need at least some handle on formulas. Yeah, that's the problem. Yeah, to make this story a bit shorter, I mean, what we need to restrict from all smooth functions on G to nice ones. And well, what are the nice ones? Yeah, the point is, let's call them E of G, and so they are, well, the E stands for entire. Yeah, so they have to do something with entire functions on the complexified Lie group, which we didn't really understand enough, but the name convinced us nevertheless, and they are characterized by growth conditions. So first of all, they are required to be analytic, real analytic. They are subject to growth conditions on the Taylor coefficients at the group unit, for example. Now, once you have it at the group unit, you have growth conditions everywhere, and they are uniquely determined by their Taylor coefficients at the group unit because you require them by hand to be real analytic. So these conditions, they are similar to the to this SR topology. Yeah. So and then I mean okay. These are technical conditions. Yeah, okay. I mean, I can write down now one lines of semi-norms, but they are fairly explicit estimates which the Taylor coefficients with respect to Lie derivatives of left invariant vector fields, they have to satisfy certain growth conditions. And then the theorem is that this E with a SR guy here, at least one, that this that on here star standard is continuous. And so we have now a nice and interesting class of functions on a Lie group, on a cotangent bundle of a Lie group, where the standard ordered star product is continuous, and also the operator n relating the standard ordering to the while ordering is continuous, and therefore also the while product is continuous. Yeah, and so I should probably stop here, but the only comment, the last comment is, well, we have growth conditions on these Taylor coefficients. And the problem is, of course, that if you're on a Lie group and you say, well, the derivatives of a function at the group unit, they should satisfy certain estimates at the group unit, then it's not really clear that if I give you a bunch of numbers satisfying these conditions, if there's actually a function on the Lie group with these Taylor coefficients, because you have global issues. Yeah, you specified sort of in a neighborhood of the unit, but whether this really becomes a globally defined function on the Lie group, it's not really clear. Yeah, and this is from that point of view is I mean, we require that they are functions. Yeah, so they should exist as functions satisfying these growth conditions, and but it's not really clear how big that space really is. Yeah, this is an interesting question. Will be how big is this space of functions, real analytic functions satisfying certain funny estimates for their Taylor coefficients on the Lie group. And in general, we don't know much about that space, but what we do know is that it contains, for example, the representative functions.
Mm-hmm. So if your G is compact and you take this Peter-Weierhoff algebra, so all that is inside.
Yes. So it's as soon as you have, for example, a faithful finite dimensional representation, as soon as your Lie group is a matrix Lie group, yeah, you have a lot of functions in there, yeah, and so, well, I mean, there are of course matrix Lie groups which are not matrix Lie groups. We know that in this situation we do not really know how point separating or how big they are. Yeah, this class, but there I would say, well, okay, if we can do all matrix Lie groups, that's already good news. Yeah, that's so representative functions, I mean, matrix coefficients of finite dimensional representations, they are all inside. Yeah. Okay, so this is an ongoing project. I mean, we have a first paper here that's with Oliver Roth and myself. That's in Mathematische Annalen. And it's of course an ongoing project now to really understand this algebra, what this thing really looks like, how many functions are there in there. This should relate somehow to the complexification of the Lie group, which is a non-trivial issue. I mean, you know that can complexify Lie algebras, but Lie groups, there might be many. There's universal complexification, and so it's not really. There are still a lot of questions left. Yeah. But I hope this gives you some inspiration that there are convergent star products beyond vector space scenarios where you have already interesting geometry. Of course, you still rely a lot on symmetries. Yeah. Mm-hmm. But but that's how you start, right? I mean, if this is how you start. And let's stop here. I'm way over time. I'm sorry, yeah, but let's
okay. Stop. Thank you so much.
Thank you. Yeah.
Yeah, this was a great talk. This is why I didn't have a heart to stop it.
Yeah, that was all your fault.
Yes, it's not my fault. I take it on me, blame it on me.
No. Mm.
And we already have first question, Tomek.
Yeah.
Yeah, so my question is related to what you said about these representative functions.
Yeah.
So let's assume that we take, instead of E of G, these algebra of representative functions and transfer it to the symmetric algebra of the Lie algebra.
Yeah.
And then we consider the formal deformation quantization.
Yeah.
Okay. is this subalgebra closed with respect to this in some sense? Or you lose everything in this completion and you cannot reduce to anything, say, of more algebraic nature?
That's a good question. I don't know. Yeah, I would suspect this sounds like a reasonable claim. Yeah, but I have no idea. Yeah, this might or might not blow up. Yeah, this is wait. If you have here a representative function, no, it should be closed. It should be a subalgebra because if you go to the differential operator picture again, yeah, this will under standard ordered quantization. This will correspond to a differential operator where the coefficient functions are these representative functions. Yeah, and this part corresponds to just left invariant things. Yeah, and now if you multiply two of these guys, then the derivatives of the left invariant derivatives acting on the representative functions, that will produce a finite dimensional subspace. Yeah, that will orbit around in this representation space, and then you multiply again represented functions together. So the whole thing should stay inside a finite dimensional subalgebra. Yeah, so no, that's a good question, and I think a nice remark. The representative functions, they should be a subalgebra together with S of G here. Yeah, and so the E is in some sense a certain completion of the direct sum of the representative. Yeah? So but it's not this. I mean, there are many ways to complete the representative functions, right? I mean, if you do it wrongly, you get all smooth functions or even all continuous functions. Yeah, so this depends really on what kind of completion you take. Yeah, but here you get a very small one in some sense. Yeah, very tiny one. Yeah.
But you can point to a function which is in EG, but it's not representative.
Well, I guess if you do the abelian case, you should be able to cook up some exponentials or something like that.
Okay.
There. Yeah, there you should get examples which really sort of are limits of representative functions. Yeah, and honest limits which are not representative themselves. Yeah.
Okay, Łukasz?
Yeah, thank you. I'd like to ask something maybe a bit less theoretical and a bit more practical, because I read some time ago that geometric quantization is not the best, but for general symplectic situation is virtually the only option. But as your talk began with the fact that the deformation quantization is done in general settings, could you say a word of how these two compare in some examples? You don't have to give the examples with description, just for geometric quantization, the algebra of observables is really small. How does it compare with deformation quantization in symplectic case?
As a disclaimer, I'm not at all an expert in geometric quantization. Yeah, but as far as I understand, there you have this first step is always very nice, finding these integrality conditions, and the trouble starts as soon as you polarize. Yeah, you have to choose these polarizations, and then you might lose all your interesting observables. Yeah? And so I think the way I would view geometric quantization is it's about quantizing symmetries. Yeah, there it's an extremely useful tool. You know that from Costan and people like that. Yeah, and so in representation theory and Lie theory, this is a very sharp sword. Yeah, that you can do marvelous things there. For physical applications, I think one of the problems is even conceptual problems is the following. In geometric quantization, you focus only on the correspondence of brackets and commutators. Yeah. And so you ignore completely the associative structure. This is not used at all. Yeah. And so from that point of view, I would say it's no surprise that you get funny artifacts concerning spectra in geometric quantization, because you ignored the structure which is relevant for spectra, namely the associativity, the product. Yeah. Well, this is of course maybe I'm a bit biased, right? I mean, this is one way I would say that there's an intrinsic problem doing geometric quantization if you're really interested in quantizing more than just symmetries. Symmetries, they are sort of dictated by their Lie bracket relations. Yeah, so that there it works fine. Yeah, but going beyond symmetries alone, geometric quantization has issues, and I view it as originating from this lack of compatibility with associative structures. I mean, I don't claim that deformation quantization solves all these problems. Yeah, and in many ways, you even historically, people used geometric quantization, smuggled in some H bar at some point, computing interesting asymptotics for H bar equals 0, and recovered or proved existence of star products doing so, yeah, as asymptotics of geometric quantization. That was maybe not so much geometric quantization, but more this Beresin-Töplitz quantization. Yeah, you get star products out of the asymptotics of those. Yeah, and so they are related. Yeah, definitely related, and maybe in the end, yeah, having now good observable algebras like that, yeah, you can then again start doing the game as you do as C-star algebras. Yeah, I mean, for you, the world starts by creating a C-star algebra, and only in the second step you look for representations of it, right, on Hilbert spaces. You make it a concrete C-star algebra, but first it's God-given abstractly there. Yeah, and the same thing one can do now here. Yeah, try to find interesting representations of these algebras. Yeah? And in some examples we have done that already, and in others we are still about to do that. And then one might even recover kind of operator representations which hopefully look familiar to geometric quantization. I don't know. Yeah, but that's also an ongoing question. And I mean, this is part 4, yeah, of my program. Study this algebra. Yeah, understand this, and understanding an algebra means understand its modules. Yeah, and understand its representation theory on Hilbert spaces, and there will be unbounded operators on Hilbert spaces. Understand their self-adjointness properties, and so on and so forth. Yeah.
Adam?
Thank you very, very much.
Thank you.
Okay, so thank you. You already answered the first part of my question regarding this representation as unbounded operators in Hilbert spaces, but still I would like to ask, okay, suppose that you succeed in representing it as an operator, so then you can consider C0 as continuous function vanishing at infinity applied to this operator, so like a functional calculus.
Sure.
My question is whether you get something which is isomorphic to compact operators, as it happens for the standard quantization, equivalent to a point.
Good question. No idea. Yeah, I mean, I guess so, because well, it's plausible, I would say. Yeah, because these kind of functional calculus and then C-star algebraic or von Neumann completions, they are very large completions. Yeah, so you lose also detailed information. Yeah, I mean, you can see it as a gain because you gain a lot of new elements. Yeah, but you also lose the information about the more specific elements, and so it might well be that you get some standard kind of C-star algebras out of that. Yeah, this could well be. I think that maybe the more interesting question is really to take that serious as unbounded operators and study the features of these unbounded operator algebras, which you cook up by representing it. Yeah? And then these unbounded operators, they of course carry a lot of information. Yeah. Understanding their spectral properties and things like that. This is but I'm not by far not the expert doing so. Yeah, I mean I know Konrad Schmödgen, for example. He loves these kind of things, right? I mean he's an expert in doing that kind of stuff. Yeah. So this would be also a project. Yeah, but to see whether the compacts arise. Yeah, one should probably do that. Yeah, this language should be able to do that.
Okay, thank you.
Tomek?
I have a question about deformation quantizations whose higher terms are not necessarily bidifferential operators. Because if you think about any one parameter deformation of a commutative algebra, depending smoothly on the parameter, you can prove that this order one alternated part of this term of order one is a differential operator. But how close is this condition of being bidifferential for higher terms to? Is there any argument showing that if you have
well, I can spoil it.
You can prove that higher terms are bidifferential operators?
No, not at all. Not at all.
Not at all.
I can spoil it immediately. Yeah, you take a formal power series of operators, not bidifferential operators, but operators with one argument, mapping C infinity m to C infinity m in a linear way, whatever you want. Non-local, funny operators. Yeah, choose a vector space basis of C infinity m. Yeah, I mean wild operators. And then what you do is the following. So given a star product which is nice, you have one. You define a new star product. Just taking this funny formal power series. So S is a formal power series of weird operators. So these are really weird. Whatever weird really means. Yeah, and the only thing you require is that it starts with the identity. And then you do the following. You start with a nice star product and define a new one by that. Yeah? This formula is again a star product, so you might need to require that these higher order terms vanish on constants. Yeah, but there are of course really weird operators around satisfying these two conditions. Yeah, non-local ones, and then the result here that will contain non-local terms. Yeah, so it's or even, I mean, whatever kind of funny terms. Yeah, you can produce new associative deformations by artificially making them equivalent to a nice one. Yeah, so this one is nice, and this becomes weird. Yeah. So sorry. So why I include that in the definition is that in all the constructions, the explicit constructions and existence proofs of Kontsevich or Fedosov or so, they spit out bidifferential operators. Yeah, they construct them automatically. You cannot even avoid that. Yeah, but that's a matter of the construction. You know? And this kind of funny thing here that shows you can spoil it if you want. Yeah. Question is why would you do that? Yeah. So but in principle it's true. Yeah. I mean you can have associative deformations with very weird higher order terms. Yeah. No problem.
Yeah, but my point is
May I answer?
Oh yes, please.
if you use careful formality theorem, you can show that that's what always happens. Any formal deformation, as long as continuous respect to nice topologies of Schwarz functions, is always given by this kind of twist, conjugating standard star product. So the one with the local, given by differential expressions.
Okay,
It's just cohomological question. Just Hochschild question, not Hochschild cohomology.
Yeah, so I expected this. Yeah. So in a sense, the way you can spoil it is a gauge transformation.
It's a gauge transformation.
Yeah, it's a gauge. I mean, that's exactly what a gauge transformation is.
So thinking in reverse. So up to these appropriate gauge transformations, you can always represent this star product in its equivalence class by differential operators.
Yeah.
Yeah.
Yes. If you, well, there might be
assuming some continuity conditions, right?
This is what you need. I mean, you have to invest a little bit. I mean, if you start with completely wild Hochschild cochains, I don't know if anyone knows the algebraic Hochschild cohomology of smooth functions. This I don't know. Yeah, but if you insist on any reasonable class, yeah, continuous in the locally convex C-infinity topology or local ones or whatnot, then the Hochschild cohomology is known, and then you can solve this exactly as Richard said. Yeah. But okay, I mean, believing in Zorn's lemma, there are many more bilinear maps around. Yeah, but why should you use them? Yeah, I mean, this is if they don't respect any sort of structure of smooth functions, then yeah, you're doing just linear algebra in some sense. Yeah, this is not interesting, maybe. Yeah. But that's one. Yeah, that's so as soon as you're sort of in the framework where you know something about the Hochschild cohomology, where this Hochschild-Kostat-Rosenberg theorem is valid, for example, for continuous cochains, then you're in a good scenario that this thing is in some sense the only bad thing which can happen. Yeah, that's the point. Yeah.
Okay, so let's wind it up. Any further questions, Richard?
Okay, yes, I do have a question. So your last example, the group, right?
Yeah.
So basically what you are doing is you are looking at certain sub-algebra of differential operators.
Yes.
Right, where you control coefficients.
Yeah.
And then look at the completion.
Yes.
So let's see. So the way it feels is that you would look at the complexification of your Lie group. Yeah. Let's keep a compact Lie group, okay? Compact and simple, make life easier. So you look at complexification, and then you look at something called micro differential operators. So these are actually differential operators which act on the sheaf of holomorphic functions.
Maybe, yeah.
So there is a completion. So there's a completion. You control of the coefficients, but there is a completion in what's the word? In this differential in cotangent direction, the linear direction.
That would be super interesting to understand.
So
I cannot answer your question, yeah, but this would be I would be happy to know. Yeah, this I mean, we sort of see that these I mean these entire functions when you take the complexified Lie group, you have a notion of entire functions, right? I mean, the entire holomorphic functions. And these guys, we suspect them, and in examples, this is true, but we're not able to show it in general, that these guys are just the restrictions of these entire functions or the complexified Lie group to the real locus. Yeah, and then of course you would have also other ways to explain the topology we have on here, yeah, because then it would be just a usual topology of entire functions. Yeah, so there are nice topologies. What do you need? The locally uniform convergence, right? I mean the compact subsets or something.
Yeah, would be enough. Yes.
That would be it. Yeah. And so that would explain this Frechet space structure we have here. You know? And we saw this in examples, but we were not able to do it in general. Yeah. But I'm pretty convinced that there is at least some relation between these two spaces. Yeah. I think if we have on the complexified Lie group, or how was it? If we have an entire function on the complexified Lie group, then its restriction, I think it is inside this one, but we don't know whether we exhaust all of them. Yeah. So this. But
probably not. We have probably no space on that.
Yeah.
But probably need terms of these things.
Yeah, but this, yeah, it might also require a little bit more information about the Lie group. Yeah, I mean, there's compactness or something like that.
Could be. Yes. Okay, thank you.
Yeah, thanks. But that's an interesting suggestion, yeah, to understand this from that point of view. Yeah.
Okay, guys, I think it's time to wind it up. So if there are no other questions, no, nobody. Let's thank Stefan again for this fascinating talk.
Thank you. Yeah.
And let me stop recording.